All right, in this lesson we're going to talk about the formal presentation of P forms and P vectors. And formal means if you go through other books on the subject, they will sometimes take a very, very strict route through the mathematics to get to P forms and P vectors. And I figured this lesson will take that strict route just for the sake of completeness and for the sake of, if you run into it, I'd like it to be the second time you see it. So we have to define a few things, and as with all mathematical formal presentations, there's a lot of definitions in the beginning, and somehow they all come together at the end to create the formal construction we're after. So let's begin with that formal constructions, those formal definitions first. And the first thing we are going to create is something we call the Sigma Transpose operator. I'll call that the Sigma Transpose operator. And it is an operator that operates on tensors. And we will choose a tensor for our example to be the tensor A, just a capital A. And the tensor itself will be bold, and it is some element of, we're going to always leave these tensors for the purposes of this discussion. It will be, let's make it a form. So it's going to be in the 0p tensor product space. It's not a form, actually. It's a tensor in the 0p tensor product space, which means it is a completely what we would say covariant tensor with p indices. So its typical representation would be A, alpha, beta, gamma, delta, etc., etc. E alpha, wedge, E beta, wedge, etc., etc. Right? And this formal presentation, it's really a tour de force of doing weird things with indices. We're going to spend a lot of time in the index environment studying different ways of permuting indices. And it's worth just sort of getting your head around all of those possible ways of doing it. I'll try to exercise every one that I know of. But the way this works is we start with sigma being a permutation, right? So sigma is a permutation. So as we know, a permutation will take, say, p objects, and it'll give you back the same p objects in some permuted order, right, like this. And this is one way of writing it. We say that sigma of 1 is some other number that's an element of the set 1 through p, right? We'll start everything at 1 and end at p. We won't use zeros right now. You can also say just sigma of 1, right, with just sort of where sigma is an operator operating on the number 1. Here's sort of a function. Sigma is a function that takes in an integer and returns another integer. But we always assume it's truly a permutation. If we don't assume it's a true permutation, we'll highlight it. But a true permutation means that we know that all of these are unique, right? And it is simply a rearrangement of these. Now, another way that this is often done, that we've already seen sort of, is I sub 1, I sub 2, ... I sub n, where I, basically, so if I wanted to have an index on A, I might say AI1, I2, I3, ... I p, say. And now I'm talking about some permutation of the indices that are available to me, and each one is identified by this I with a subscript. Now the problem, of course, is we're dealing with objects that ends up with subscripted subscripts, right? So alternatively, I could have written A sigma 1, sigma 2, sigma p, like that, or even A sigma 1, sigma 2, ... sigma p. And all of these things have their flaws, right? I mean, this one here, the problem is that you're writing a lot horizontally, and that gets a little confusing. Here, you have to have some kind of textual break between the things. This one has subscripted subscripts, but they're all connected, and you might actually, if you had a permutation, you might want to write sigma of 1 is defined as I sub 1, right? Something like that, or actually, that would be your basis for creating little subscripts and superscripts. All right, but we'll use these different notations at different times in this formal lecture. So, we start with a permutation, and our permutation, we'll call it sigma. And so P of sigma is an operator called the Sigma Transpose. And if we have A, which is an element of the, in this case, the completely covariant tensor product space with of rank P, I guess that would be rank 0P tensor product space, we want to define the operation, the sigma transpose operation on A, right? That is going to produce another, it's going to produce another tensor. So A is a tensor, and as such, it's a mapping that's waiting for a variety of vectors. So we'll say it's waiting for vector v1, vector v2, all the way to vector vp. Now notice how this is going, right? This is always kind of confusing, so I will actually take a good look at it this time. Here, what I mean by v is boldface vector v with the subscript 1 is the name of the vector. Right? So that's the name of an element of the underlying vector space V, right? Which is the T10 tensor product space. And so it's the name of it has the subscript. This subscript is not a tensor index. It is simply the name. And so if I wanted to write vector v1 in component form, I would have to do something like this. I'd have to write v1 sub mu e mu, where this is the name of the vector. And I'm doing this because I don't want to go alpha, bravo, dot, 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 delta, because I want the number of these things to be assigned to each of the vectors I'm putting in there. So I need to number the vectors, and if I'm going to number the vectors, I need to create a name that has a number in it. So I'm choosing to make that number a subscript. I suppose we could have done something like this. We could have said, okay, this guy is V, and to make its name work, I could have put the 1 up here, right? Someplace we don't usually see a subscript. That would have worked too. But the books that I recommend people read, Bowen and Yang, which is really the primary source for a lot of this, that's not how they do it. They do it this way. They do it this way, and we just have to keep track. And usually there's boldface here. I'll try to boldface stuff sometimes. Anyway, so A is a completely contravariant, completely covariant tensor. So it's feeding on a string of p vectors because it's the 0p rank, and so it's waiting for 0p vectors to come back and give a real number. So what is this thing? This is an operator, the sigma transpose operator, that operates on A. So it's going to produce another tensor, and what is that tensor going to be? And the definition of this new tensor is that it is a tensor. It is also an element of the same tensor product space, but it is going to consume. If I put in v1, v2, dot, 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 vp, the output is going to be the original tensor with just the inputs shuffled around according to the permutation. So it'll be v sigma 1, v sigma 2, v sigma p. Now make no mistake, this guy here is a different, this guy here, is a different tensor than A. But this different tensor is defined such that all I would have to do is take A and reshuffle the inputs, and the answer will be different, right? Reshuffling the inputs will give me a different answer, and I'll show you why in a moment. So it is a different tensor. This is a different tensor than this. Because whenever I give this guy v1, v2, vt, and vp, this guy returns the same tensor as though I had given it a different collection or a different ordering of its inputs. That's a different tensor, and that tensor is called the P transpose of A. Now, we can do this in a very specific example. Let's consider A to be an element of the 0, 2, right? A 0, 2 tensor product space. So in this case, therefore, A would be A1, 2, E1 tensor product E2, right? Plus, well, let's say plus nothing. Let's say this is it, right? That's the tensor we're after. It's just one component, A12, E1, E2. So that would mean that A21 equals 0, A11 equals 0, and A22 equals 0. So I'm just picking out a random tensor from this tensor product space. A nice simple one with one component. It's only got one component in the completely covariant rank 2 tensor product space, the 0, 2 tensor product space. So I've assigned these values, and I'm just looking at this guy. And the reason is I want to illustrate. Now we have to choose sigma. So sigma is going to simply be the permutation 1, 2, 2, 1, right? I just flipped the two. That's going to be sigma here. So in this, using our notation, sigma 1 equals 2, and sigma of 2 equals 1, or sigma 1 equals 2, sigma 2 equals 1, something like that. So then I'm going to define P of sigma of A acting on V1, V2 is going to be A acting on V of sigma 1, V of sigma 2, which in this case is A acting on V2, V1, like that. Well, A acting on V2, 1, that's A. What is A? Well, A is A1, 2, E1 tensor product E2. And it's going to be acting on V2, V1, like that, which is going to be A1, 2, the component, times E1 mapping V2, and E2 mapping V1, like that. Now, that turns out to be exactly equal to, I could have, instead of swapping these two out here, this turns out to be the same as if I had swapped the two basis vectors, right? So I could have written that as A1, 2, E2 tensor product E1 acting on V1, V2, right? I could have done it that way. So just to show the equivalence, that the effect of this permutation operator by reshuffling the indices, I'm creating a new tensor. This is the new tensor, right? This guy here, let me draw it in red. This guy here, acting on V1, V2, that's what this is. So this guy here actually is that, right? So this transpose operator, the sigma transpose operator, has the effect of taking A. The sigma transpose operator on a bunch of vectors has the effect of taking A, reshuffling the basis vectors, and operating on these inputs. And that meets this definition. That satisfies this definition that it's the same as taking A and reshuffling the inputs. So if I take A and reshuffle the basis vectors, I can create P sigma A and then operate on two vectors, or I can define the sigma transpose of A as A operating on the shuffled vectors. It's really the same thing, but this is the definition now of how P sigma A functions. I could have used a slightly different notation, I guess. I could have said P sigma of A acting on V1, V2 equals A12 of E sigma inverse of 1 tensor product E sigma inverse of 2 acting on V1, V2. I could have started from that idea, and then I would have said, well, that equals that would equal, say, this new tensor, P sigma of A. It would have to have its 2-1 component, right? That would equal the 2-1 component of E2, E1. That's because of inverse sigma 1 and inverse sigma of 2 operating on V1, V2. See here in this method, I'm trying to keep these without shuffling them, right? In the time I just did before, we shuffled the arguments, and then this becomes A sigma 2 sigma 1 E2 tensor product E1 V1 V2. So there's another. So this is another way of sort of producing the same result, right? Where we instead of shuffling the indices, we shuffle the basis vectors. But it's all the same. The permutation operator. The whole goal is that its core definition is always going to be this. It's always going to be this. And we will use the permutation operator to start defining other operators. I guess the way I should say, so where does this, I should add this one point. Where does this end us up? This ends us up with the definition of the components of the permutation operator. So P sigma A, it has components, and I'll use this other notation for the components, I1, I2, IP. So this guy is, remember, P sigma A is an element of the P exterior power, right? So, I'm sorry, what am I saying? Jesus. It's an element of the, not the P exterior, I'm getting ahead of myself. It's an element of the tensor product space, 0P. So it can always be expressed like this, I1, I2, IP, where we sum over all of these indices. So we sum over I1 with I1, I2 with I2, and it's this massive sum. So the component, this component here, we can, using this logic, we can define that component as P sigma A, I1 to IP, equals the component of A, but now it's I sigma 1, I sigma 2, down to I sigma P, like that. So this is sort of the definition of this tensor by defining it through the components. If we can define the components, then this defines the actual tensor itself, or at least one representation of that tensor. So this is the logic for the transpose of, or the sigma transpose of a tensor. All right, so now we're going to define another operator on tensors called the symmetrizer, right? Like the symmetrizer, SP, operating on a tensor T, will return the symmetric part of the tensor T. And T, just like before, we're going to presume is part of a 0P tensor product space, right? It could be a P0, but it has to be completely covariant or completely contravariant for what we're doing here. And so the symmetric part of a tensor, T, is this will represent the general tensor, but in a particular basis, it will look like this. The tensor T will be given its indices, I1, I2, all the way through IP, but I'm going to put parentheses around it. The parentheses means that this is the symmetric part, right? This is just the symmetric part of T, right? See, T is a tensor in this space. It's an arbitrary tensor in this space. The operator SP on T returns something we're calling the symmetric part of T. And so when I put these parentheses here, when it's telling me is I'm really looking at a different tensor. I'm not looking at the tensor T. I'm looking at SP of T. In other words, I could write, no, first of all, let me finish this. This I have to write as I1, I2, to IP, right? Because remember, whenever I have these components, whenever I write components, the method I'm using, I like to keep the basis vectors with me. So in order for this tensor to be a tensor, I need to have the basis vectors too. So you're still summing over all of these things, but now these parentheses tell me I'm dealing with this. So another way to have written this would have been the tensor SP of T, its components I1, I2, to IP, E, I1, IP, like that. Right? So here I'm highlighting the fact that we have a different tensor, and it's the symmetric part of T. So now I don't need the parentheses, because the parentheses were there to tell me that we're dealing with just the symmetric part of T. So I like to go through this because I feel like the benefit of these lessons is a lot more to get you comfortable with all the wacky notation that's out there in the different books. And somehow going through that is illuminating. Some people don't agree with that, by the way. Not everybody likes that approach, and that's fine. It's really just the approach that worked for me over the years. It's just that this material is spread across so many different books that you can't expect to reconcile them all without some effort. But that effort is illuminating, in my opinion. Anyway, so this is the symmetric part of T. Now we've done nothing but notation here, so now we have to actually define this thing. So the definition of the symmetric part of T is going to be, I'll write it back with the parenthesis form, I1 to IP, EI to IP, and it's going to equal the components, right? These components we're now going to put right here into a formula, 1 over P factorial times the sum over all permutations of T I sigma 1 to I sigma P, right? That is that will be the component, and then it will be E I sub 1 tensor product tensor product E I sub P. Now this thing may look a little bit confusing. This is a sum, and this is the actual original tensor, and the components of this tensor, the indices, are shuffled by a permutation sigma, but we're summing over every possible permutation. Every possible permutation of these indices will be summed over, and that component will be added to the one before it. So you're adding up the component of every possible permutation of these indices. So I have to start with a selection. Say I started with the selection, 1, 3, 1, 2, 5, 6, right? I was saying we're dealing with a six-dimensional space. So we have 1, 2, 3, 4, 5, 6 different dimensions out there, and I'm looking for the 1, 3. I'm wondering about T symmetric part 1, 3, 1, 2, 5, 6, right? Notice this isn't a form, right? So we can duplicate indices here because it's just a member of the tensor product space. So this guy, that's the one I'm interested in. So I now have, but now I'm going to shuffle these guys over every possible permutation based on this. So the first one, I1, I sub 1 equals 1. I sub 2 equals 3, I sub 3 equals 1, I sub 4 equals 2, I sub 5 equals 5, and I sub 6 equals 6. So now a typical permutation would be to leave all these things alone, right? So the first permutation would be identity permutation, and then therefore this first term would be T1, 3, 1, 2, 5, 6. Then I might have a permutation that just switches the first two, right? So to that I need to add T3, 1, 1, 2, 5, 6. Then I might have a permutation, well, not might, I will have a permutation that swaps just the second two. So to that I add T1, 1, 3, 2, 5, 6. And I do that until I've done every possible permutation and add those things all up, divide by p factorial, which is the total number of permutations, and that would be whoops, I got to make it very clear. Once I've calculated this guy, right, I pause, I add it to the next one, right? I add it to the next one. So I'm adding all these guys up and then dividing by p factorial. In the end, you end up with a number, and that number is the component of this, of E1, E2, E1, tensor product, E2, tensor product, E5, tensor product, E6, right? This particular basis vector inside this tensor product space, this particular basis vector here, that component is calculated using this method I just explained. And I do that for every index possible here, and I should end up with an expression for the symmetric part of T. And what's going to end up happening is if all I do is take some permutation of this, right, some permutation of this and put it here, the fact that I'm summing over every other possible permutation here is going to return to me the exact same component for a different basis vector. So if I did this whole calculation for these guys, I end up with this number times this basis vector. Now, if I switch it and I do it for 3, 1, 1, 2, 5, 6, some easy permutation of this, I'm going to end up with the exact same component, but I'm going to end up with the basis vector is going to now be well, I guess this should have been a 3 to begin with, right? E31. So E3 tensor product E1 tensor product E1 tensor product E2 tensor product E5 tensor product E6, like that. So the basis vector is going to change, but the component's going to be the same, and that's what a symmetric tensor is, right? The value you switch indices, but the component doesn't change. Now the basis vector will change, and so there will be a different component for each, not different basis vector, but for each different basis vector that's not a permutation, just a simple permutation of some other basis vector. And in this case, if you're dealing with a 6-dimensional vector space, if all I have to do is I have to start with something that's different here. So if I started with 1, 3, 3, 3, 5, 6, that is not a permutation of this, so that one will give me an independent component. So this is the symmetry operator, or the symmetrization operator. Now, an interesting thing to look at is what happens if I calculate this guy. The sigma permutation of the symmetrization of a tensor T, right? So this guy is going to be a tensor. This thing is a tensor in the 0p tensor product space, and so is this, right? So this will, whatever this guy is, it will have p indices, I1, I2 to IP, and those indices will be the sigma operation, right, acting on the sum that we just calculated, right? It's sort of 1 over p factorial times the sum over all possible permutations. I'll call it pi now because I've used sigma, because sigma is a permutation specifically built, the p transpose, the sigma transpose, and so I have to choose a sigma to create a sigma transpose. So I've already chosen a sigma, so I have to have a dummy permutation for the summing over all the permutations of, and we figured out that this would be t I of pi 1, I of pi 2, dot dot dot, I of pi p for all the possible permutations. But now we know that since you're summing over every permutation, right, taking a sigma permutation, a sigma transpose of this thing, is not going to make a difference because you're going to sum over every permutation anyway. So you're just summing over a permutation and then permutating by sigma, you're still going to hit every permutation once. So the point being that it has no effect. This will not change the value of this component because you're summing over every permutation. So affecting one in the beginning doesn't make a difference, which is what we expect. We expect that the symmetric part of T will be unaffected by any P transpose operation, right? So this is going to, so I can write P sigma SP of T equals SP of T. Oops, I never introduced parentheses, SP on T. Now, now be clear, this is not the same as P sigma of T equals T, right? That's not what we're saying. It's the symmetric part of T that is unaffected by the sigma transpose, and that's what this is. This is just the symmetric part of T. Right. Likewise, now we can also do the anti-symmetric projection operator. That's what I was fumbling for, right? Projection operator, right? SP is the symmetric projection operator, right? I was calling it the symmetrization operator. That's not right. It's the symmetric projection operator, and this is the anti-symmetric projection operator. Anytime you see anti-symmetry, it gets a lot trickier. I don't know, a lot trickier. It's just it's messier. It's more. It involves determinants instead of just sums and things like that. So this one, yeah, this is a little more intricate than the other, but you know, everything is kind of straightforward and logical, right? The idea of an anti-symmetric projection operator, I'll just write down its definition. Its definition is, we'll call the operator KP instead of SP. So SP was the symmetric projection operator. This one will be KP. So KP will act on a tensor, and again, T is an element of the 0p tensor product space. It could be the P0 tensor product space, like I said, but we illustrate this usually with forms instead of vectors. I don't know why, it seems to be the common illustration. But this thing is going to be defined as 1 over p factorial times the sum over all permutations sigma of epsilon sigma, which is the Levi-Civita symbol with the permutation sigma, times the sigma transpose operator executed on T. So we've already defined this guy, right? This is plus 1 or minus 1, depending on whether sigma is an even permutation or sigma is an odd permutation. So we've already defined that. This is a sum over all permutations, and this is a normalization factor, which is important. We'll see why in a moment. So that's the definition of the anti-symmetric operator. So we do know that the anti-symmetric projection operator, at a minimum, must produce an anti-symmetric tensor, just as the symmetric projection operator produced a symmetric tensor, which means that an anti-symmetric projection operator, the components change sign when you flip the indices, or equivalently when you take a basis vector that has exchanged bases in it, it should change sign. So this guy, if we gave it a anti-symmetric tensor to begin with, right? If we gave it a tensor Q that was already anti-symmetric, then it should return Q. But what do we mean by Q is anti-symmetric, right? Well, that means any sigma transpose on Q, right, should return the sign of the sigma permutation times Q itself, right? That's all it does. Is any sigma transpose on Q just returns Q, because what you're doing is you're shuffling things, right? You're going P sigma on Q acting on V1, V2, Vp. You know that that has got to equal Q acting on V sigma 1, V sigma 2, V sigma P. And you know that that thing just simply equals the sign of sigma Q V1 Vp, right? That's the definition of what it means to be anti-symmetric in your arguments, is, you know, you reshuffle the arguments from here to here. All that does is it just changes the sign of the result, depending on whether sigma is an even or an odd permutation. So basically, the point being that this, if this is true, right? If this is true for Q, we assume it's true for Q, then we are expecting the anti-symmetric part of Q to equal Q itself, right? We're expecting this to be true. And we can check that with the definition without too much trouble. This is a question mark, I guess. So this has to equal 1 over P factorial times the sum over, say, all the permutations sigma of E sigma P sigma Q, right? That's this definition right here, where T is Q. Now Q has this property, though, right? So P sigma of Q equals the Levi-Civita of sigma on Q, right? So this is 1 over P factorial times the sum over all permutations of epsilon sigma, but P sigma of Q is epsilon sigma again of Q, right? But we know that epsilon sigma times epsilon sigma has to equal plus 1. It can't equal anything different. So this is going to equal 1 over P factorial times the sum over all permutations of Q, right? But that's just adding Q up P factorial times, which is P factorial over P factorial times Q, right? Because this sum here equals P factorial times Q. So this just equals Q, right? Which is exactly what we wanted to show here. So this anti-symmetration operator acting on an anti-symmetric tensor returns an anti-symmetric tensor. So that's good. Now there is So we do know that the antisymmetric operator acting on a tensor yields an antisymmetric tensor. So we know that this thing is going to live in this vector space, right? So for any tensor you give it, this guy here is going to return an element of that space. The open question is, does every element of this space, the antisymmetric part of some tensor? Right? And the way we ask that question is we ask it by saying, is the sigma transpose of an anti-symmetrized tensor T? We know that that is the sigma transpose of 1 over p factorial times the sum over all the permutations pi. I have to introduce pi because I've already used sigma here, right? And that is epsilon pi of p pi operating on t, right? And it's the sigma transpose of that tensor. Remember, this is a tensor here, right? So this guy here, this is a tensor, and you're just summing up, you're taking a linear combination of all these tensors, and you're taking the p transpose of that. And everything's linear, so when this is a sum of a bunch of tensors, this just goes right into the sum in a linear fashion. Well, what does that actually equal? Well, that actually equals the sigma transpose. I'm going to execute that linearity, right? Over pi e pi, and then I put the sigma transpose here over the pi transpose like this, and then let's see, then we go 1 over p factorial sum over all the pi's, and then we realize, okay, this is Levi-Civita pi p, and we just replace this with a single transpose, because transpose, this means transpose with pi first and then sigma second, and that's just another permutation, right? Pi sigma is simply another permutation, and in fact permuting over all pi's is still going to permute over all permutations here, because it's just like before, right? We permute over all pi's, but it's pi first, then sigma. As long as we hit every pi and sigma is just one permutation, we're still going to hit every permutation. Okay, so we've got that. But the other part that's important is that this thing I'm going to rewrite now as epsilon, as the sign of the sigma permutation multiplied by the sign of the sigma pi permutation. And you notice that'll always equal the sign of the pi permutation, because the sigma permutations are the same, so they'll multiply out to 1. But the reason that's nice is that it lets me write it this way: 1 over pi factorial, sum over all possible pi, sine of sigma pi, p sigma pi t, right? And then that lets me write it this way. I just pull that e sigma out, because remember, e sigma is not summed over, right? This is a sum over pi, so this is just a constant number. 1 over p factorial, sum over all pi, e sigma pi, p sigma pi t, like that. But as I was just saying before, this sum is going to be identical to the sum over pi of epsilon pi p pi of t, like that, because we're summing over every single one of these things. And therefore, this whole thing ends up being meaning that p sigma kp t equals epsilon sigma kpt, which means it's antisymmetric, right? So this is the definition, right, of our antisymmetry. And so this is saying that the sigma transpose of anything that's been already antisymmetrized will just be antisymmetric in the sense that it will just be the sign of the sigma transpose, the sign of that transpose, times that antisymmetrized object. So this is how the antisymmetric tensor is defined. But we will also have a formula for the components of this thing, which is, I guess, sort of the meat and potatoes of it. This guy will look like this. Let's say J1, J2, ... JP, but this time we put brackets around it. So brackets are telling me that I'm dealing with the antisymmetric part of T, right? T is its own tensor. It's neither symmetric nor antisymmetric necessarily. Kp of T is the antisymmetric part of T, and I put brackets to indicate that, whereas parentheses would be the symmetric part of T, which would have been SP of T. So SP of T would be this, J1, JP with parentheses. Okay, but we're not looking at that. We're looking at the antisymmetric part. And the component, the basis vector associated with that, of course, is J1 to JP, like that. And it's still an Einstein sum over everything. But to calculate this component, we have a formula, and that formula, as you might expect, is more complicated than for the symmetric one. But it has to do with the generalized Kronecker delta function, I1 to IP, J1 to JP of T, I1 to IP, and then the final component is EJ1 to JP. And so what you're seeing here is this generalized Kronecker delta function is what calls out the sign for the component. So that's the part that makes all the antisymmetry work. And we learned about this in our lesson, in an earlier lesson, what the generalized Kronecker delta function was. And then this is the component of the underlying tensor that we are antisymmetrizing, and this is the basis vector. Oh, so I wrote my basis vectors poorly. The basis vectors should look like they're tensor products, right? So there should be tensor product E J1, E J2, tensor product E JP, J1 tensor product E JP. So this is how you calculate the component of the antisymmetric part. So you would literally write T J1 JP. So you choose J1 and JP because you're trying to calculate a particular component. So I might pick a series of indices. Now in this case I do have to pick indices that are all unique, otherwise this generalized Kronecker delta function will return a 0, right? Because you remember how that works. You can't duplicate indices anymore when you use this generalized Kronecker delta function. So this guy is going to, say I chose 1, 3, 4, 2, 6, something like that, then that establishes what these indices are here, these J indices, and that establishes what the basis vector is that you're interested in. And then inside here, you sum over everything else. You sum over everything else. And that sort of captures the notion of summing over all the permutations in the basic definition. And so that is how you execute the antisymmetric projection operator. Oh, also note here, I should point out that when this is all said and done, the way we've defined everything, this antisymmetric part of T is being expressed in the basis of the tensor product space, right? So this ultimately, of course, there's no reason why it shouldn't be. It's still expressed. It's still a member of the rank 0p tensor product space, but it's expressed in that basis. But it's a completely antisymmetric tensor. So we already know that this thing is a member of a subspace, the P, the subspace of forms, of P forms, right? So this is an example of us landing in the P-form subspace, but we're kind of using this basis right here, which is redundant, right? We would now, knowing that we can combine, because of the nature of the components, we can combine a lot of these things together and end up with the strict basis, right? Which would be EJ1 wedge EJ2 dot 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 EJP, where J1 is always less than J2, which is less than J all the way dot 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 to less than JP. So that's an important point to make, which is that it's the same tensor, it's just being expressed in a different basis. And in fact, this basis here that it's being expressed in is excessive because there's too many basis vectors. They're not all independent. So it's arguable this may not even really be a basis, so to speak. It is, but it ends up landing in a subspace where you can actually create independent basis vectors just for the subspace. And the reason this is important is, again, we're going to talk about the transformation of antisymmetric tensors eventually, whether they be covariant or contravariant. And that transformation property is different if you express it in this basis, this sort of overly broad basis. I guess I'll call it a redundant basis, or the strict basis. The transformation properties are not the same because we're using a different representation of basis vectors, and the transformation properties we've learned for tensors are always for these tensor product spaces, not for these exterior power spaces. Okay, so in this lesson we introduced the Sigma transposition operator, or the Sigma transpose operator. We introduced the symmetric projection operator and the antisymmetric projection operator. Now that we have these definitions down, we're going to use that to do the formal construction of P vectors and P forms. And we'll do that next time.